Hello.
Yes, sir.
Yeah, so good. So, so tell me, how have you gone through the previous day's lecture?
Yes, sir.
Any doubts, any questions, anything from the whole course? Any doubts, any questions, whatever? So, are you guys comfortable with the definitions of P and P and yeah, mostly P and P, these two things?
Sir, I was looking online. I found NP hard.
Yeah.
I didn't get that.
Okay. So, what is NP hard? So, okay. So, I didn't exactly. I mean, NP hard is basically NP. Okay. So, so you have this P, right? You have NP, right? Now,
Yes.
what is so? What did I say? I told that okay. So let me define it in a slightly different way, not different way, kind of same way. So I will not call. So in the last class, I defined a problem as how do I define a problem? I defined a problem. So and let I will use a different letter here. L be a problem. It is a subset of 0, 1 to the n, 0, 1 to star, right? So this is L stands for language. So usually we call a problem a language. A problem is basically called a language. Okay, it's a pretty useful notation to use because a particular element, okay, x in 0, 1 to the star is called a word. Okay, so you have the universe 0, 1 to the star. But yeah, I hope you guys are not confusing 0, 1 to the star, right? I mean 0, 1 to the star is all strings of 0, 1. I am not defining a particular length, right? I am not defining a particular length. So any of them is called a word. And if you think of the English language or whatever language you're comfortable with, right? It is a collection of words, right? So in that respect, a problem is called it's basically a language, which is a collection of words. Okay, good. So this is the formal definition. Let me ask you one thing. Do you have any course on theory of computation or automata theory or logic in your undergrad BStat program?
No, sir.
No.
Next time we'll have a course on advanced algorithms.
You have course on advanced algorithms
Next time.
next time, but
Yeah.
not on this logic and all, right? Okay. What
No,
about
sir.
in MStat or something? Not much.
I don't think there is.
Okay. So if you are interested in learning this formal stuff, okay, so this comes under the area of computability theory, computability, or automata, or even to some level logic. Okay, and if you guys are interested in learning about it formally, it's a beautiful subject, and this subject is I mean, uh, it has a unbelievable connections to a lot of things. For example, computability theory is now one of the most powerful techniques to prove lots of problems in number theory. Okay, so I mean, like it's a very big, not only from the point of view of computability and so on and so forth. This has a lot of connections that comes out there. Okay, in something called a model theory that is related to this and so on. So if you are interested, I can suggest you a book. There's a book by Dexter Kozen. Okay, there are a lot of books, but I personally like this particular book, Dexter Kozen on automata theory and logic. And I mean, it's available online. It's pretty easy read. I mean, it's very well written, well explained. Of course, the problems are ranges from very easy to extremely hard. But if you are interested, you can read them, but for yourself. So there you have all the formal definitions, all the formal notions of how you define all of these structures. So coming back, so in this course we will not go into so much details. So we have these languages L, okay, and so these are called all of these kind of stuff are called the basically they're called classes, okay, or language classes, okay. Language class, meaning it's a collection of languages. Okay, so in some sense you can think of it, all of them that we are talking about, P, NP, there's some lots of other things. Collection of languages, right? And the main idea is that, okay, so we will say something like, okay, when is L in NP? Okay, L is in NP if for all X in L, there exists I told you that it is easy to, what is the definition of NP that I gave you? There is a easy, so let's start with a simple one actually maybe. What is the problem with in NP? Okay, or what is the L in P? L in P is if for all, okay, so maybe not for all. So let's say there exists a algorithm, a polytime algorithm, A, such that A of X, such that for all X, A of X is A of X equals to 1 if and only if X is in L. So basically it says that if the language is in P, that means there is a language, there is an algorithm, you feed it X, and if it is in language L, it will output 1. If it's not in language L, it doesn't output 1, it outputs 0 maybe. And it is polytime, meaning the runtime of A on an input X can be upper bounded by a polynomial, fixed polynomial. Okay, so what does this mean? When is an A, so what do I mean by this statement? Okay, that means that there exists a polynomial. Now this polynomial is fixed, okay? It is not dependent on X. There is a polynomial P such that for all X, A of X, maybe, yeah, A outputs or so all X, for all X on input X, the algorithm A runs for less than or equal to poly in. So this poly of course is a poly in a particular variable, right? Poly in Y. So poly in size of X runs for less than or equal to poly in X time. Okay, time of course you know. Time I don't mean time in seconds. Time means number of steps. Okay, so this is the definition of formal definition of P that one can write. Okay. Now, what is the formal definition of NP? Now, this is a bit more tricky. Do you guys recall what was the NP definition?
We can check if the answer is correct in polynomial type.
Right. So L is in NP, means the definition is that if and only if, okay. Okay, so maybe I should write it very carefully. There exists a polytime algorithm A, and for all X in L, meaning if X satisfies the language L, okay, this is a bit, be a bit careful over here. For all language X in L, okay, there exists a phi of X. So this is called you can think of this one, I will use it in a different color. So this you can think of as a proof. Okay, it's a witness, a proof or witness, such that A X, A on input, sorry, am I there? Hello?
Yes, sir.
Some of my internet showed that my internet is unstable. Okay. A of X and phi of X is 1. Okay. Sorry. Yeah. There exists. Yeah. And okay, so this is two statements. Okay, so this is one statement. If X is in L, then there is a proof, and if X is in not in L, there doesn't exist any phi of X, or I should write it differently. For all y, okay, A of X y equals to 0. So let's think what is it formally saying. Okay, first statement is that this is a polytime algorithm. Okay, fine, makes sense. It's polytime. Now what are these? So I give you, let's think of L to be something like a vertex cover. Okay, so question is that, so what is this L? L is a set of all graphs with vertex cover of G to be less than n by 10, or size of G by 10, say. Okay, size of V of G by 10. Okay, now this is a language name. What does it mean? That you have to convince me. Say, let's say that, or say I have to convince you. I am the student in some sense, right? You have asked me that here is the graph G. Is the vertex cover, does there exist a vertex cover of size less than V by 10? Okay. How will you do it? How will I do it? If the G actually satisfies this quantity, if actually G is here, I can just give you the vertex cover, right? The vertex cover is the vertex cover, you can have an algorithm that takes the vertex cover, the proof that the vertex cover, and you'll yeah, fine, good. Whatever as you have given me, I am convinced this is actually a vertex cover, and the vertex cover size is less than the number of vertices by 10. Good, done. But if the G that you give me is not in this language, meaning it doesn't have a vertex cover of this size, then can I ever convince you that G has a vertex cover of size less than 10? I should not be, right? So if X is not in the language, or means in this case V is say G is not a vertex cover, G doesn't have a vertex cover of size less than n by 10, then whatever I do, I might try to cheat you, I might give you some random proof, I should not be able to convince you. Okay, is this clear? This formal definition?
So what is exactly the proof over here? Proof or the means phi x or the y?
Phi x is nothing, it's called a proof, but it is basically a witness, or basically a support statement. It depends on the algorithm, right? So for example, if G is a vertex cover, okay, so if this is the language that I'm talking about, right? Now you give me a particular graph G, okay, so what will happen if G is in, so let's call this a language to be L, right? If G is in L, what does it mean? That G has a vertex cover of size of vertex, number of vertices by 10, right? So I will say that, okay, good. If you give me this language, the phi of G in this case, right, phi of X is nothing but the set of vertices that forms that is a vertex cover and is of size less than V of G by 10. Okay. So I give you that vertex, set of vertices. Okay. So if you so you have given me
a solution.
this solution set, right? Yeah. So if G is in a, don't think of it solution. It's like a. So what are the questions? Your question is that is G in L? That's the kind of question, right? So, right.
Yes, sir.
So I mean, the question is that is this graph has something, or so you say that something like you give me a number and I will tell me is this number a prime number or not?
Sir, is 5G something like a proposed solution which we are going to check?
Exactly. It's a proposed solution. It's a proposed solution in the case that if so it is sometimes called a prover and a verifier. Okay. So think of it this way. Okay. Here is a verifier. Okay. Or if you want to think of it in some way, you can think of this as the teacher, or you can think of it, you can think of this Akbar and so on. Okay. And here is the prover. Okay, the prover is basically nothing but you can think of a student or Birbal. Okay, now, so and there is a language L. Okay, always, and the teacher wants to know is X in L. Okay, so the teacher says, okay, student, can you say is X in L? Now, of course, the prover or the student or the Birbal wants to cheat. Okay, that is something that always everybody who is trying to prove something tries to cheat. So the prover will reply back, say something like, okay, if he replies back no, then fine. The prover's goal is to kind of convince. What is the prover's goal? Prover's goal is to convince the verifier that X is in L. But the verifier is also clever. Okay, so he's not a dumb person. So the idea is that the prover can give a lot of arguments for that thing. So this set of arguments, we call it as phi of X. Okay. Now the idea is that if X is in L, if the answer is correct, then the prover will be able to answer in such a way, will be able to give such answers, maybe give the proof such that verifier is convinced. Okay. Fine. So here, so think of it this way again, that if L is that vertex covered thing, the verifier wants to check if a particular graph is in the language, or if particular graph has the vertex cover less than some threshold, and gives to the prover. If actually X is G is in the language, that means if actually G has a vertex cover of size less than the threshold, the prover can say that, oh yeah, see, here is the vertex cover. Here is the proof that it is a vertex cover of size less than the threshold. Fine. And in that case, I mean, the teacher or verifier just has to kind of verify that, okay, are you giving me the correct thing? Yeah, okay, good. So this is the correct proof. And I have check it quickly and I'm convinced that yeah, you are right. But if X is not in L, or in other words, if the G does not have a vertex cover of size less than the threshold, then the prover can give any kind of garbage arguments, doesn't matter what. I have no clue. But whatever that argument is it, the verifier should not be convinced. verifier is not convinced. Okay. So, I mean, the prover cannot prove that X is not in L. Okay, the verifier is not so, but the prover's goal is, you can think of it as like it's a one-sided thing. The prover just wants to cheat. Or if you want to think of it in a way that, I mean, say the verifier is the judge and the prover is the lawyer, okay? And the judge wants to check, has this person or is this person honest? Okay, if that person actually is honest, then the judge, or maybe let's think of it not in the honest, okay? If the verifier wants to check, the judge wants to check that is this person has done a fraud, okay? Now the idea is that if the person actually has done a fraud, there should be a proof for it, right? And in that case, the prover or the lawyer should place that proof in front of the verifier or judge, and the judge will say, okay, yeah, I got it. He has done a fraud. But if that person is not done a fraud and he has somehow been wrongly implicated, then the lawyer can give lots and lots of crazy arguments. But still the judge should not be able to be convinced that the person has done a fraud. Okay. So this is exactly NP. NP is the class in which if a language, if a X is in the L, if a X is an element of the language, then there exists a valid proof. If X is not in the language, then we don't have a valid proof, or no proof is a valid proof. Is this clear? Is this
Yes, sir.
somewhat okay? Because I am going to possibly, I mean, you will be a bit confused after what I'm going to say here. So see here, there is a slight difference. Okay, so let's think of it. What is a P? What is the language P? What is the language P? No, sorry. What is the language P again? In the language P, if we see this whole thing on top, a language P is such that if X is in the language, if and only if. Okay. So in some sense, you can think of it that, I mean, in the language NP, okay, it is impossible to convince someone that X is not in L. I am not even expecting it to happen. The verifier's job is not to convince someone that X is not in L. But the verifier's job is to convince someone that X is in L. Okay. So let's take an example. Maybe this is slightly better thing. So here is a language called primes. Have you heard of this language? So primes is basically the set of all numbers n in the natural numbers such that n is a prime. Now this has a long story. I will tell you just now. Okay. So if I take a number n and I ask, is n part of primes? What do I mean? I want you to check if a number is a prime or not. Okay. Now, of course, the first is that, okay, the most is that is primes in P. Meaning, is there a polynomial time algorithm that given a number will check that, oh, this number is a prime or this number is not a prime. Okay, that is possibly the most, the big question, right? And I don't know whether you guys know or not, but the number theory in general, this kind of primes and factoring and all of those, they have a strong relationship with cryptography. Have you guys done anything in cryptography? Heard of anything in cryptography?
So not in course, but
Not in
I
course.
internship in RC course.
Okay. Okay. I mean, so maybe I don't know who will be teaching you the next advanced algorithms course, but if and when it comes out, I mean, you might see some nice proofs there. Okay, where you can see that this number theory and cryptography, and what is cryptography? Is the subject of securing any transactions. Okay, like we are talking on the internet, and the very fact that nobody can easily tap our thing and hear what we are saying is done by cryptography. Okay, and it has a long story. I mean, we can have it later on, but this is a kind of very important question that comes up. If I give you a number, is it a prime or not? Okay. What do you think? Okay, can you find out something like this? Okay, so okay, fine. We don't know how to do that. I mean, not right now, but see, we know that P is in NP.
Sir,
Yeah,
how many steps do floor function takes?
floor.
Yes, sir, floor.
I mean, how to find a floor of a what? Of a real number? Think of it as constant.
Then this problem can be solved in linear time.
Why?
If floor function can be solved in order 1 steps, then division can be solved in order 1 steps.
Very good. What is the algorithm you will tell me?
Start from 2 and check if this number is divisible by them.
Very good that you brought this question up. I'm very happy. Okay, here is an algorithm. Okay. So for I equals to 2 to P or 2 to N, if I divides P, then report not P. Report N is N. Report N is not prime. Else report okay, and else report N is prime. Or at the end it is forget this, not else. Yeah, just report N is prime. If you basically complete the whole stuff and you report N is prime. So this is what you mean, right? Go over all the elements from 1 to N, check if that number is divisible by P into P minus 1, right? And if N is divisible by that number, then you report it is not a prime, of course. And if for none of them you have reported it is not a prime, then at the end you should say, oh, okay, good. So now the N is not divisible by any number. It is not. It's a prime. Do you think this algorithm is correct?
Sir, but the input size is just
Yeah. I'll come
like
to that. Good, very good point. Somebody has. I mean, I am happy that you guys are engaging with me. But in correctness, is this correct? Actually, the algorithm is perfectly correct. There is no reason this algorithm is wrong. This algorithm will certainly give you the right answer. There's no question about that, right? Because if something is not a prime, then it must have a factor less than itself. But what is the running time? So you can say that this algorithm is correct. There's no question about that. Okay, this is perfectly correct. But question is that what is the runtime? See, the runtime is order n. I am thinking that this whole process can be done in one step, okay? Order one step. Dividing something, checking whether it can be divisible by something can be done in order n steps. So the runtime, the total number of runtime is basically ordered n. But is this polynomial? Is this algorithm polynomial?
It's exponential.
It is exponential. Why is it exponential? Because see, I don't, yeah, go ahead.
Size of input is log n.
Exactly. What is the input size? See, if I have to give n as an input, the size of the input is a binary representation of it. It's log n, right? Maybe it is log to the base 10. I don't know what, but something. It's a log to some constant, whatever array you are writing it. Okay, whatever representation of n you are writing, unless you give n as a unary. When you tell you n, you said, ah, great, good. Go and, I mean, I will give you n by giving you n balls. That is what happens, right? You specify n as a decimal or in binary or something like that. And in that case, so we can call this one to be log to order of log n. And in that case, the runtime becomes 2 to the power order the input size. So you'll understand a bit more better that this is something that, by the way, Indian Army, for example, has to handle this question regularly. Okay, I will give you a number on, say, 1000 length decimal representation, 1000 digits. Okay, I will give you a number in 1000 digits. Okay, makes sense. And I want to check, so this is a number n, and I want to check, is n a prime? Right? So whatever algorithm that you gave me just now, this will say that, oh, okay, good, go for all of them. But the n is a 1000-digit number. So what is the value of n? Or rather, n can be as large as or 10 to the power 1000. Or 10 to the power 1000 is not a joke, right?
We can take up to root n.
Fine, root of this, how much is that?
10 to the power 500.
Is 10 to the power 500 an easy job? Right? So you will basically say, okay, root of this will be 2 to the power order input by 2. Input size by 2. It is still exponential, and more importantly, it is impossible. If this number is something that is called as, this is more than the number of molecules in the universe, and some kind of random crap is told about this. But the main idea is that this number is just out of our reach. Our computers will just not be able to find out this solution of this in the next 500 years if you keep on running this algorithm. Okay, and so you see why the exponential can be better. Instead, if someone can come up and say that, oh no, see, I have an algorithm. If somebody says that I have an algorithm that runs in time, say size of the input size to the power 10. In that case, the running time therefore becomes 1000 to the power 10. Now the 1000 to the power 10 is basically
10 to the power 30.
10 to the 30. The 10 to the power 30 already is a number which is way better than 10 to the power 500. right? I mean, 10 to the power 30 is also a big number, but it is still something that is almost a supercomputer can do. 10 to the power 500, no way any computer can do. Okay. So this algorithm primes, right now I have not seen a proof of primes within P. Okay. Yeah.
So how does floor being a constant time function imply that division is also constant time?
I mean, nothing, it doesn't mean anything. But see, one thing that you can do, it's not a constant, it is also kind of a order, login kind of stuff like that. But it's always thought to be a, I mean, it's a polynomial stuff. Okay. I mean, you can divide something in log of n number of some things. I mean, how do you divide something, right? How did you divide it when you were in class 2? You had the division algorithm, right?
Yes.
You can do the same thing now in the computer, and it can be done in log of n number of steps.
Okay, so
Okay. I mean, exact that algorithm will give you a, it's not an order one, but it's a polynomial. So my main thing is that this doesn't matter. Problem is that you are running this for loop itself for too many number of times. Right? And as you say that if, when we are talking about polynomials in general and not just n to the power n square or n cube or something, we are not too worried about a few polynomial factors here and there. A polynomial times a polynomial is also a polynomial. Right? So,
Sir, we are considering this to be an exponential in the input size, but like with respect to the actual number itself, it is in
It's-
polynomial.
yes,
So
but
like so why are we seeing it in like input size? That I'm not able to understand.
everything is done in terms of input size. Everything that we have done till now has been done in terms of the input size. Okay, because you are given something, you are given an input, right? The input has been encoded in this form. So I have told you an input and I've encoded that input in 1,000 digits. So your algorithm, I mean, 1,000 digits is very easy, good, and computer can go and read 1,000 digits without any problem, right? But can a computer read 10 to the power 1,000? Of course not. And that is exactly why I have specified the number in 1,000 digits. So here is a number that can appear in real life, and that is given as this is the encoding, right? I mean, I have encoded something. So the computer doesn't even know how n. Computer just gets this 1,000 digits, and it is supposed to output something. The runtime of an algorithm, this is something, a runtime of an algorithm is always in terms of the input size. Always, this is something that you can take it. So that's why if you see that however I defined from the beginning only, that P, right? P is a language for which I told it's a polytime algorithm. And what is a polynomial time algorithm? If it runs in time p of size of x, size of x is the input size of x, right?
Yes, sir. Yes.
I mean, every time we did that, by the way, when we were dealing with BFS and DFS, we told it's a linear in the input, where because the input size is an adjacency matrix, adjacency list, which is m plus n. If the input is n square, an adjacency matrix, then it is much easier. Okay, everything is done in terms of the input size. Okay, now you might say that why polynomial? I mean, in some sense, you can see from here what does polynomial means, but this is a bit of a philosophical discussion that we can go into. But that what is solvable? I want to go into this thing. Okay, I mean, like there was a lot of these questions about which problem. So maybe, yeah. So in 1995, sorry, in 1895, Hilbert, okay, gave 10 problems, or 10 or 20 problems, I think. No, I think 10 problems. He specified 10 problems and he told that these are the problems that were supposed to be the guiding problems for the next 100 years. Okay, so these are like Hilbert's 10 problems. You can search it in the internet and you will get it. Hilbert's 10 problems. I might be wrong here. It might not be 10, maybe 20, but something, some number, small number of problems. He told that, oh, this is the problem that will guide us from the next 100 years. Many of the problems have been solved. Many of the problems are still open. Say something like Poincare conjecture, some problems in Hodge theory. Some of them are pretty simple, like some Diophantine equations and all that was easily solved. One of the questions that he asked was, remember that time there is no concept of computers, right? There's no computers, but the logic was there. And then he asked which problems are solvable. Now this question is a lot of a philosophically packed question, because you don't know things like what does a problem mean. You don't know what the solvable means. Okay, and okay, he didn't specify exactly in this term. I think he defined it in terms of Diophantine equations. But still, the basic idea is that overall it comes down to which problems are solvable, which problems are unsolvable. What does unsolvable mean? Is the problem unsolvable? Does it mean that, I mean, I have not been able to solve it? Does it mean that it's unsolvable? Or are there problems that are just not solvable? Meaning, we might, I mean, it's not like it's hard. It is actually not solvable. And nobody can solve it. Even God cannot come and solve it, something like that. Are there problems like that? Or in other words, say if you are more, say, coming out from the, so everything in mathematics is done from axioms, right? You start with the Peano's axioms and goes for it or something like that. So basically, I think that if you start from Peano's axiom, is all number theory problems that you can state in their life be solved somehow or other, can be answered somehow or other. Okay, so this was the question that was proposed as one of the 10 problems. And this particular problem was answered by Gödel. Okay, by Gödel. And he basically proved that, and this is a beautiful thing. If you want, you should read this paper, okay? It's called the Gödel's incompleteness theorem. And this is considered to be one of the biggest contributions of the last century in theorem. It's a theorem, it has nothing to do with any assumption, anything. Okay, and I mean, when it was voted and all, I mean, while most of the people told that in the last century, E equals to mc square of Einstein is possibly the biggest contribution ever to human world in the last century. This one was voted the second most important one. And it's beautiful. What he proved is that, okay, what he proved is that no problem, okay, let me just say it and not spell out very clearly here, is that if you start from any axiom setup, so Peano's axiom is just one example, okay? If you start from any axiom, doesn't matter what the axioms you start from, And as long as the axioms are not self-contradictory, okay, then there exists always a problem that will remain unsolvable. That means there will always remain a problem which cannot be answered using the set of axioms or formal proper deductions from the axioms. And most amazing thing is that you can't even know whether if I give you a problem, you can't even tell me whether the problem is solvable or not solvable. So this was a I mean the massively big problem, big beautiful thing. But note that he defined it, he kind of proved it without actually defining solvable. It was this, he proved it through the axiomatic world, but he didn't say what is the solvable problem. And over the next few years, many people started saying, proving lots of things, what is solvable. Okay, so and then there's this whole work that kept on happening called what is solvable. And finally, in some sense, it was, so of course, by the time Gödel was like the big boss in logic, and people were suggesting, proposing things, and various people were coming up with great ideas, and it was not very clear what was going on. Okay, so then the first there was a guy called Church, who basically gave this thing concept called in the world of called lambda calculus. And then Turing came and gave a very came a very mechanical way of proving something. He gave this thing called Turing machines. And later on, I mean, and there's some more actually. Okay, and finally, it was proved that whatever Church has proposed and whatever Turing has proposed, both of them are same, equivalent. Okay, so if a problem is solvable according to the definition of Church, the problem is solvable according to the definition of Turing. And so that came as the Church-Turing thesis. Now, I should state here that this is a thesis. What does the thesis mean? See, there is no formal definition, there is no proof that this is solvable. Okay, there is no proof that this is solvable. Church-Turing thesis says that, okay, I think this is solvable. And you start with that, and kind of people accepted it, and it has been challenged many times, but right now it's kind of accepted. Okay, it is not a theorem. It is not a theorem. Okay, it is an attempt to define what is solvable. Okay, so they prove that the lambda calculus and Turing machines are same. That's a theorem. But the fact that this is the final definition of solvable is not a theorem. It's a thesis, it's a proposal, it's a hypothesis you can think of. And I mean, I will tell you that many times this thesis has been challenged. In particular, Feynman, when the concept of quantum computing came in the picture, I mean, I don't want to go into this whole object of quantum computing, but when it came into the picture, people asked, okay, using a quantum computer, can you prove more things? And people had to go back, see it, and prove that no. Even using quantum computers, you cannot prove something that is not solvable using Church or Turing. That was proved. So this is, in some sense, yeah, it's a plausible definition. Plausible definition, okay, for solvable. Now, nowadays, in most of the places, if you go and try to find out the Gödel's incompleteness theorem, you will find a proof of Gödel's incompleteness theorem, which starts with this and then goes and proves that, okay, this is not the whole set of all problems. So that means there is a set of problems that are not solvable using Turing machines or something. But that's the wrong or easy way out, because Gödel's proof is a theorem. It has nothing to do with any definition of solvable. He actually proved it set theoretically. Okay, so now this one was the concept of definition of solvable, and okay, so after this, for some nearly 30 years somehow, and this is something I don't understand very well, that for 30 years people were more interested in hierarchy among non-solvable or not solvable problems. Now it is something like, you know, that there are different definitions of infinity. It is like that. Okay, all of them are infinity, but there is infinity of real numbers is more than the infinity of natural numbers, right? So you can have a hierarchy of infinity. Similarly, people were more concerned about hierarchy among non-solvable problems. This one was a crazy, I mean, it is a very well developed subject that came up with. It was mostly from the logic world, and this is what came out to be known as computability. I must say that, I mean, I could never appreciate this particular subject that much. I mean, I was not that abstract in my thinking to appreciate the concept of hierarchy on the non-solvable problems. But the technique that they have used is beautiful, no doubt about it. Mathematics there is outstanding. Okay. But then there was another group of people who were a bit more algorithmic, or the computers coming up, algorithms coming up. People are saying, okay, fine, this is one area, but what about things that are solvable? Is there a hierarchy in the solvable problems? Meaning, is a problem more solvable or more easily solvable than another problem? So is there a hierarchy in solvable problems? Or in other words, which problem are easily solvable? Now, of course, this also came up as a long of different questions, right? This is in some sense, you can think of it as a philosophical discussion that goes on. And defining this question, or saying that which problem, is there a hierarchy and all, was kind of easy to some level. Why? Because the definition of solvable problems had this thing of Turing machines. And Turing machines naturally, I mean, I will not go into the definition of Turing machines at all. Okay. But this kind of naturally gave a hierarchy to the solvable problems. Okay. And using that, the whole concept of, you can define things like time complexity, you can define space complexity, and so on. Now, note that this, although it was formally being defined, these concepts were kind of there. That is the reason, to find GCD between two numbers, we have an algorithm that goes back to Euclid over 2000 years ago, right? Or we have an algorithm of multiplying two numbers. And if you think of it, the algorithm is not obvious. Ask a normal person to prove that, see, whatever you are doing, prove that it is correct. If you have a number 1, 2, 3, 4 multiplied with 5, 6, 7, 8, I mean, you kind of do things like, okay, 1, 2, 3, 4, and 5, 6, 7, 8. You basically write 8 into 4 is 32, 3, and so on and so forth. Then have a cross, then write something, then have 2 crosses, and then write something, and then have 3 crosses, and then write something, and then you add it up, and you say, oh, this is the number. This is an algorithm, and that algorithm has been there for ages. And people will not understand why we are doing this. I mean, what is this thing? Actually, this is nothing but add 1, 2, 3, 4, 5,678 times, and then add it. Why don't we do that? Because we had a sense of time complexity beforehand also. we had a sense of space complexity beforehand also. We were basically trying to optimize our process. Okay, so algorithms, the time complexity was there. The notion was there among us for many, many years. And it is not just the Greeks or something. I mean, to go look into things like, say, representation theory, if you look into things as number theory, all of these things had these things really built into it. Okay. And right. So, but here it was formally the time complexity and space complexity was defined. And then the question came about what is the meaning of easily solvable. And that time, the notion of P was introduced. P is the set of all problems with time complexity polynomial in input size, right? And it was kind of argued that this set is the set that we think of it as easily solvable. This is a easy to compute problem. So this notion has still stuck with us. Of course, nowadays with computers coming up, actually, we have started asking a lot of other questions also. Okay, but this notion is there. So this is all formally defined and everything is fine. But is P an easy to compute problem? Is it actually an easy to compute problem? This is up to you to decide, or up to. But this problem, this problem P is perfectly formally defined. Okay, and so always the goal is to kind of put, if you want to solve some problems nicely, the goal is to put P in some problem in P. Okay. So is this thing kind of clear? I mean, it is a very philosophical discussion, and I would love to go on discussing on these things. This is a beautiful area where logic, mathematics, and lots of other concepts actually comes in together. Any questions?
So I had asked the definition of
Right. You have asked the definition of NP-hard. I will come to that. Yes. I'm coming slowly. Don't worry. Okay. So good. So then you have the definition. So we had this P, and now we had the NP. Okay. So NP is the problems for which there was whether something exists or not. So I can ask you a question, and maybe I will not answer it right now. I will let you guys think about it, and I will come back and do it next time. So is primes, so primes is in NP. Is this question correct or not? Okay, think about it. Okay. Or can you come up with a proof of it or something like that?
So your primes has to be like not in P.
That I don't know, right? Right now you gave me an algorithm that is not in P.
No, but I'm saying the primes problem is not in P.
Why?
Because in order to check if a number is prime,
Yeah.
I need to see divisibility with all primes less than that number.
Okay, but is it the only thing that you can do?
At least I have to do that.
Not necessarily. You remember there were some things like this fact of Fermat's little theorem and so on and so forth. Okay, so if P is a prime, so this is in 2 to the power P is congruent to P mod or whatever, something Q to the power P is congruent to P mod Q, right?
Right, but that is the other way around.
No, hold on. So maybe that's what we can do, right? No, sorry. Okay, so I will take up number P Q. I will raise it to the power of P. Raising a number to the power of P is very easy, by the way. Okay, why? Because how many times you have to multiply? Q, then q square, then q to the power 4, then q to the power 8, something, 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 then some, we will come very close to a power of p, which is 2 to the power t, which is less than p, and then I will, I mean, basically do it slowly, because there I can do 2 to the power t plus 2 to the power 8, and so on, right? So I can, so this total number of multiplications is logarithmic. So I can take a prime number q, raise it to the power p in log p steps, check whether that number is congruent to p mod q. If that number is not p mod q, I know that it is not a prime, right? So see, I have not done the simple things. I have not done whether something is divisible by, if p is divisible by a number or not. I don't know the factor of p. I have no idea. Now, problem is that this can be one start. But the problem is that this is not an if and only statement. So, I mean, if it is not, throw away. We can do that. But I can choose other q. Maybe by choosing 10 different q's, I might be able to throw away everything. Maybe by choosing log p number of q's, I will be able to just eliminate all possible non-primes. So in other words, I'm saying is that the algorithm doesn't have to follow a particular pattern. There can be lots and lots of crazy techniques that can be there. Okay, it is not at all obvious. Yeah. Okay, so proving something is not something is very hard. In fact, I will tell you a bit more before I answer your questions about the NP hardness. Okay. So once I have defined this P and NP, then we had this thing of, okay, I have these two languages, L1 and L2. They can be anywhere, I don't care. Okay. So by the way, they can, I mean, I should maybe draw some picture over here. Okay. So here is this picture of solvable, say. Okay. It is sometimes defined as recursively enumerable. Sometimes it is called computationally enumerable, something like that. And then within that, there's some lots and lots of hierarchies there. Inside that, there is this area called NP. There are problems here, by the way. Lots and lots of problems here. Okay. And inside that, there is this area problem called P. Okay, so there's a P, NP, and solvable. Fine? Okay. Then we come to the next thing, and this is something that we have done earlier in some sense, you guys have done actually. If I take you two languages, L1 and L2, okay, then I can say, yes, which one is harder? Is L1 less than or equal to L2? What does it mean? So this means that if I give you for all x in L1, okay, for all x in L1, right, there exists a x prime. So sorry if I made a mistake, complete mistake. For all x in 0, 1 to the star, there exists a x prime, which I can, which is basically kind of can be attained by applying a algorithm, a polytime algorithm to x. Okay, by polynomially massaging x, I can produce x prime such that x is in L1 if and only if x prime is in L2. So remember that this is exactly what you guys did when you reduced the vertex cover to ILP. You told her, oh, give me any graph. I will encode it as a problem in ILP, such that if the graph has a vertex cover of size t, so that means this graph's vertex cover is less than or equal to t, say, then the ILP, the minimization problem, has a solution of size less than or equal to t. So this is called a reduction. Right? So are you guys convinced that this is something that you have done when you reduced various problems to ILP?
Yes, sir.
Right? This is exactly what you have done. Okay. Now, in the last class, I kind of told that there is this concept of NP complete. Right? What are the NP complete problems? NP complete problems. So I tell that okay, and L hat is an NP complete problem if for all problems in NP L is less than L hat. Okay, that means this is a problem that is kind of harder than L. So by this basically, this particular thing in some sense basically says that if you want me to solve L1, solve whether X is in L1, I will basically end up and giving you a problem L2 and say that go and solve that. If you can solve L2, I am done. Right? So think of it that, I mean, you have a black box, a machine that can answer if X is in L2 or not, or anything is in L2 or not. All you need to do is that you start with an X, convert it to something, and asking whether X is in L1 is basically asking whether X prime is in L2. Right? And I kind of told that, okay, you have this NP completeness, which basically means that a particular problem is harder than any other problem in NP. Okay, so actually what I told is slightly wrong. Okay, what I meant was, so this is actually called LP hard. Any language that is harder than all the problems in NP is called NP hard problems. So these problems in this picture, a few of them can be here, like ILP, few of them can be here also. So there is no reason to believe why the NP hard problems have to be in NP. I can have a problem which is way harder than anything, but all I know is that this problem is harder than every other problem in NP. Okay, so this is called NP hard. And what is NP complete? It is just a slight difference. Okay, NP complete is exactly the same thing, right? So we say that L hat is NP complete, or is NP complete if, first of all, two things are satisfied. First of all, exactly what is written there. If L is in NP, for all in NP, L is less than or equal to this one. And second, L must itself, sorry, L hat must itself be in NP. Okay, so NP hard and NP is just a little bit off. Okay, so a problem which is NP hard and which is there in this NP is called NP complete. So if I have to draw this picture a bit more differently, okay, so let me see. So I have this huge NP over here, and I have a class of problems here which is NP hard, right? Out of which the problems that are within NP and NP hard, these are called the NP complete. Is this clear?
Yes, sir.
Yeah, so NP hard and NP complete are not very difficult to see. But the important thing is that, I mean, you have to understand that this is all thanks to the formal reduction. So when somebody says NP hard or NP complete, people are very vague about it, okay? Because, I mean, it's not too much difference. So people abuse notations and sometimes call NP complete as NP hard, sometimes call NP hard as NP complete. Okay, so it is not something too different here. Yeah, so the interesting thing possibly is the fact that what Cook and Levin proved, so this Cook and Levin proved in, I think it is 1972, that, so they proved that there exist problems or languages, there exist languages that are NP complete. Okay, if there is something within NP that is the hardest among all the function systems. There are problems inside NP which is harder than every other problem. Now, so maybe I will. What we have proved is that not proved. We have claimed. Okay, I mean I will say that. Okay, you can think of this theorem as by Cook and Levin that ILP is NP complete. I have not given a proof of it, and because the proof of it is not very easy, and you have to go through the Turing machine definition. Okay. So there is another function called SAT. Now, are you more familiar? I mean, have you heard of or worked with Boolean formulas or something like that? If it's a Boolean formula, does it ring a bell to you?
Like composing Boolean variables with the and.
Yeah, if I say, yeah, this one, does it make sense?
Yes.
You have guys seen it in previously?
Yes, sir.
You have seen it, and you have also seen this one, right?
Yes, sir.
And good. So what SAT is actually, let me define SAT. It's kind of important function that will come up here. Okay. So what is SAT? SAT is basically a formula, Boolean formula. Okay. And but I will just define it a slightly easier one. So think of it. It's called a CNF, a conjunctive normal form, which basically is nothing but so if I have a set of variables, okay, and I want that one of them must be satisfied, okay, and of the x4 or x1 bar or x2 and something else. A formula of this size is called a conjunctive normal form. Okay, it is I mean anything can be written as that, but you can think of this as a and of or. So there's the and of things which are or. So in other words, this is called a clause. Okay, these are the clauses. These are clauses. So in every clause, and your goal is to check. So okay, so if I want, so I have a phi. So phi is a CNF. Okay, and I want to see. So phi is satisfiable if, so let's say the phi is on variables x1 to xn. Phi is satisfiable if there exists an assignment. So xi is being put to true or false and so on. If for all I, you can put xi to true and false, such that so phi evaluates to true. What does it mean? So it is like, okay, I want you to satisfy these clauses. And in all the clauses, at least one of the variables must be satisfied, must be turned to true. Okay. So this is called a satisfiable thing. So SAT is a language which is all those fees such that fee is satisfiable. Okay. I mean, there are other definitions of SAT also, but this is possibly the easiest definition of SAT you can think of. It's a Boolean formula. I mean, if you don't like this particular Boolean formula, it's a bit more restricted. You can take any Boolean formula. That's also fine. And checking whether the Boolean formula is satisfiable is something that right? It is something like, you say, if you want to buy a computer or buy a something, some gadget, a phone, what do? You go to the Amazon or go to some store or something and tell them what? Give me a phone with hard disk, this or this, or space, this or this. And either it has to be maybe an Apple product or a Android product. And it has to be blue or black, but not pink in color, and something. So you're giving a collection of constraints, right? It is exactly like this. You give me, so the X size maybe are true and false depending on the phone specification, right? The X1 is maybe, okay, it has to be either red in color or blue in color or green in color. Or if you don't give me red, and you give, or you if you either you, yeah, I mean, if, this is not a good example, I mean, but you understand, right? I mean, or you can give me this following thing, in which, okay, fine, I will not, it is fine if you don't give me red, or if you find maybe you don't give me blue, but in that you have to give something else to me. So some kind of a constraint that you do, and accordingly the store owner or something will say that, oh, okay, good, so here is a phone that satisfies all your constraints. Okay, so do you see that there is a similar structure between the SAT and ILP? So SAT is also a collection of constraints, but they are Boolean constraints. And you're asking that, is there something that satisfies this, such a weird constraint? Maybe you go to the store owner and ask some various weird constraints that will, oh, no such phones exist that satisfies all of you. Right? ILP also has a similar flavor. You're trying to optimize, maximize or minimize something, but it's not even clear whether any assignment of the variables will satisfy this constraint, will satisfy the AX is less than B kind of structure, right? Okay, so this is the definition of SAT. Is this definition of SAT somewhat clear?
Yes.
What about others? They lost me?
Yes, sir.
Okay. So there is SAT and there is ILP, and these are, you can think of as the two basic problems that are there. Okay, and both of them are NP complete. I mean, there are a lot of them are NP complete, but this you can think of as the, I mean, the Vartes cover is also NP complete for that matter. Okay, so SAT is NP complete. Okay, ILP is NP complete. Now, if you want to prove something else is NP complete, okay, so to prove a language L is NP complete, how do you do that? You will first find out another language L bar. That is, the first step is that find a language L bar, find a language or problem, okay, L bar or L hat such that L hat is known to be NP complete. Okay, and secondly, you prove that L hat is less than or equal to L. Okay, note that you can say that, okay, why to choose a language? Why not just start from SAT and prove everything? Or why don't we start from ILP and prove everything? Yeah, technically you can do the same. You are right. But sometimes proving that SAT reduces to a language might be harder than proving ILP is reduced less than a language. Okay, or maybe you know vortex covered is an NP complete problem. Maybe proving that vortex covered is less than a particular language is easier than proving ILP is less than a language. Okay, so so by the way, I think I will stop now. The sixth assignment will be uploaded today. It will not be due for some time, so you can take your time to work on it. But I will again, I have requested you guys to read section 8. Okay, so whatever we did today was a bit more formally doing things that was done in the last class. Nothing much else. Okay, and this is kind of yeah. So particularly in the writing it everything in terms of the language and so on. One thing that was I'm happy that you guys posed this particular problem, that why is a simple language not in why doesn't it give it to be a prime? Yeah. The other thing is that I have asked you to prove, where is it gone? Okay. Yeah, this question. Okay, this question, please try it out. This is very important. Okay, you will understand a lot more by trying to solve this one. Is primes is in NP? Okay, and yeah, so sorry, in the reduction, in the things, in the assignment, there will be a lot of some reductions that you have to be done, proving something is NP complete and so on. So I suggest that do it through some practice here, discuss with us, try it. I mean, we will try to help you more and more. On Saturday, we will have a class which will be mostly be discussing problems, and we'll discuss. So please be interactive, because this particular part, I don't want to be very, I mean, unless you guys try it out, something, learn, think about it, you will not be able to get much out of it.
Sir.
Yeah.
Sir, to prove a language L is amply complete, in these two steps will imply that it is NP hard.
Ah, good, right. Okay, good. I made also. So you have to also prove that L is. You have to
Yes.
also prove that L is in NP. Right. Third thing will prove L is NP. So first two steps will prove that L is NP hard, and this will you have to prove L is in NP. Third step. Right. So let me stop here. Just before that, I should say that we were talking about this language primes, right? Now, this is a big thing. You guys are all too small to know, but in 2002, 3 guys from India, they are Agarwal, Kyle, and Saxena. Agarwal was a faculty at IIT Kanpur. He's still there, and Kyle and Saxena were his master students. They proved primes is in P. It is a big, big, big problem that they proved. Okay, so we know that primes is in P. The proof is not hard, but not something that I want to do it in this course. So if you do an advanced algorithms, you can, whoever is the teacher, you can ask them to prove this thing for you. Okay, but
Sir, yeah, about that, like advanced algorithms is an optional course. We were wondering if you could take it next semester.
I mean, I cannot commit anything right now, because as you know that, yeah, I don't know exactly what will happen. I will get back to you guys. The reason is that, it's first year courses have just started. I don't know whether you guys know or not. Just
Yeah.
started this week or last week. So now having 3 semesters packed into 1 year in some sense. Yes.
Uh-huh.
So things are a bit crazy right now. So what will
So
happen?
are you also taking first years?
I am also taking first year, not B-STEP. I'm taking master MTech students first years.
Oh,
Okay, but I will still like to know a thing. I mean, this is something you guys can all leave, of course. I mean, it's done. At the end of the course, is there a representative for your course? Maybe, or whoever is it can take a responsibility. I would like to get some feedback from my course. Okay, it can be unanimous. You can be completely. Secret stuff. I don't need to know who has given me what feedback. The reason I'm asking for the feedback is not particularly for the subject that I'm teaching or this one, but because this is a virtual thing, right? This is also a new experience for me about how to teach this thing on Zoom and all. So a feedback will be very useful. So what you can do is that if you guys want to give me a feedback directly, email me. That would be great. Okay. Any suggestions that you have? What did you like? Any part of the code that you would like to improve, both in terms of the subject, content, lecture delivery, or teaching style and something like that. Okay, anything. And if you don't want your names to be revealed, what you can do is that you can find a representative, give it to that person. I don't need to know your names. You just give me the anonymous comments. This will be very highly appreciated. Okay, and it will be very useful both for you guys and for your follow-up other batches and all. And the other thing is that since one of you told that you want to attend the advanced algorithms course, I would really request you to find out how many people are actually interested in advanced algorithms course. Okay, and accordingly we can have a talk about it.
I know at least 3 are.
Okay, I mean, maybe can you just have a email among yourselves and basically
We'll inform you.
yeah, and inform us, because the courses have not been allocated for next semester, so things are pretty
Yeah,
confined.
that's why we wanted to tell you first, because like if already get allocated, then there's no point asking.
Yeah, so I understand that. I mean, technically I'm still teaching this semester, but yeah. So by the way, I'm not the only person who can teach algorithms. There are a lot of other people who can teach algorithms. Okay, and maybe it's a good idea if you hear the algorithms from somebody else. It gives you a different perspective to algorithms. Yeah, you have your seniors with whom you can discuss. They have, I think, they were taught by someone else. So yeah, so please give us a feedback so that I can pass it on to the deans of it at least when it comes about this particular thing. I mean, my job for this particular course was to inform you guys as much as I can, motivate you to the subject of algorithms. I find it to be a very beautiful subject, which is very mathematical, and I think any person with a logical bent of mind will really appreciate it. But something that possibly is not that well advertised in ISI. So if you guys like it and want to continue learning it, at least I will ensure this advanced algorithms course is offered. Whether I teach it or not, that's a different issue. Okay.
Okay, thank you, sir.
Yeah. Thanks.
Sir,
Yeah.
Thing.
Yeah.
So you asked us to prove that primes is an NP.
Yeah.
NP complete.
No. I didn't ask
But-
you to prove primes is NP complete. I thought primes is in NP. That's it.
Okay. Yeah, that makes more sense.
Yeah. I just told you to prove primes is in NP.
Yeah, but you added that last. Oh, that was for general problems.
Which one?
You added a point now, which Diptonil pointed out.
No, but that is for proving NP complete.
Yeah, that's not for the primes problem.
No, that's not for the primes problem.
Okay.
I'm just saying how to prove a problem with NP complete, and this is how to do it. Okay.
Sir,
Yeah.
why is the Indian Army interested in this primes problem?
Oh, because as I told you, oh, good. So I will talk about it actually maybe next class. The primes is a very important problem. And in fact, for example, one big problem that happens in the, that is in the important in the defense world and all, because as I told, every cryptography stuff starts with a prime. Okay, starts with a prime. So the goal, one of the big goal in the world of for defense, you can think of, okay. So in defense, in cryptography or something, cryptography is to find a large prime. This is easier said than done. If I ask you to find a prime, give me a prime on 2000 digits, will you be able to do it? This is not easy at all. And the reason is that how do you check? I mean, you can come up with a particular function. Okay, here is a number on 2000 digits. It's a prime. How will I check it? How will I verify it? Unless I have an algorithm to solve it. So if so people, what they do is that they come up with lots and lots of crazy ideas of how to find out or how to prove a particular prime or produce a prime. And most of it comes from, say, very complicated algebra or number theory kind of stuff like that. Okay, and at the end of the day, once you find one, so if you are smart enough to come up with a way of producing a lot of large primes, okay, you are a millionaire, or you will be kind of picked up by the defense immediately, because it's like an extremely important thing. Defense, anything in cryptography starts with a prime. Okay, so primes problem is a very big problem. Okay, so we will talk about it a bit more in the next class, maybe on Tuesday. Okay. Good. Any more questions, doubts? I mean, I can take some more questions. Okay, so if not, let's stop now. Perfect. Okay, so I'm stopping the share.
Thank you, sir.
Yeah, so there will be class on Saturday, but it will not be a class. It will be more of a problem solving stuff, and some of the doubts that you had earlier, it will be kind of cleared up. And okay.